Good morning, everyone. Before starting this lesson, I would like just to spend a few seconds to thank you for being here right now at this time this morning from your home. And I guess it is not easy for anyone to attend a lesson and face exams in this way, but I think that you should always be try to be passionate with your work. So not please do not stop yourself with um, by this kind of situation. So don't let anything be an obstacle for your education. And I think that me and the rest of the teachers will do everything possible to facilitate your learning, and so we will go ahead. And so okay, let's say tell me a little bit. Who of you is still in your pajamas? You can respond if you want. So it is a little bit difficult. Okay, perfect, Emanuele. So I think it is a okay, perfect. So we can see the positive side of the thing and see that see to this lesson as a way to have breakfast together, each one with his or her own tea, milk, or coffee. So the positive thing is that there is not even the possibility that I pay. So very well, I would say. So we can go. We can start this lesson. This is a lesson. I think another right easy lesson about learning tasks in machine learning for signal processing. So previous in the previous lectures, we made an introduction to machine learning for signal processing. What is the machine? What is the meaning of machine learning? What is the meaning of signal processing? We saw and the meaning of machine learning for signal processing. We saw some kinds of general applications in which we can apply all the methods and we can find all the methods of machine learning, and we can find all the problems of signal processing. So now we have another view of the problem. So we go a little bit into detail, but still staying as a higher level. So we can have a view of the learning tasks of machine learning that we started in the last lecture, and we go a little bit into detail of the tasks that we're going to to see in this course. So with the task that we're going to study for machine learning for signal processing. So we can also provide some example of the task that we are going to see. To simple problems, to problems of just some examples to understand what is the meaning of these tasks. So basically, we start from the one slide that we showed the last lecture, not the last week. So here is a view of the main tasks for machine learning. So the main machine learning approaches, and as I said, we have 4 approaches. Many books, many in the literature, maybe you can find 3 main approaches, which are supervised learning, unsupervised learning, and reinforcement learning. And semi-supervised learning is sometimes divided in part in supervised learning and some part in unsupervised learning. But I prefer uh, to, to, to classify semi-supervised learning as a fourth approach, because its tasks are sometimes are completely different from the tasks of supervised learning and unsupervised learning, and there are a lot of new tasks, new algorithms that are completely independent of supervised learning and unsupervised learning. So I prefer to divide this group, and so we can focus on supervised learning. Supervised learning has some tasks like classification and regression. We go in a little bit into detail in these kind of things. We have, for example, application like image and audio classification, event detection, diagnostics of medical images, and so on. We can have regression problems like prediction, forecasting, modeling, estimation, and so on. For the unsupervised learning, we have two main tasks, which are the clustering and dimensionality reduction. We will go a little bit into detail also of this kind of tasks. In particular, the clustering is like something related to application like image segmentation, anomaly detection. Dimensionality reduction is some kind of feature selection, but we go into detail of the explanation further. We have the semi-supervised learning, which can be seen as some semi-supervised classification, regression, and clustering. So we can have subtasks of supervised learning and unsupervised learning. And then we have the reinforcement learning, in which we have application in the field of robotics, autonomous driving, gaming, resource management, and so on. In this course, we mainly focused on supervised learning and something related to unsupervised learning. In particular, we focus on classification tasks and regression tasks, which are, I think, the most basic and also popular tasks in machine learning. And we will see something related to dimensionality reduction, related to unsupervised learning. But in the last part of the course, using deep learning, we can have the possibility to go a little bit into detail of also other tasks that are related to unsupervised learning and semi-supervised learning. But we don't introduce the main machine learning algorithms for clustering, for instance, because there are also other courses in Sapienza that can go into detail in this kind of problems, and the same for reinforcement learning. So basically, we go a little bit into detail of. So we will see algorithms related to classification, regression, and something related to unsupervised learning. Okay, so basically we will deal with the semi-supervised learning tasks, as I said. So we have classification tasks and regression tasks, and dimensionality reduction. So we will focus on these three general the general tasks. So today I would like to explain. I would like to give you a high-level view of these tasks. So we can see, I would like to explain you what is classification, what is the meaning of regression and dimensionality reduction. So we start from classification. So we can say that the goal of classification is to assign an unknown group of input samples that is called a pattern to one of a number of classes that we consider to be known. So we can understand this kind of meaning by taking some example. For instance, we can consider the X-ray mammography. So we have an image, and in this image we have a region that indicates the existence of the presence of a tumor. So the goal in this case is to predict if this tumor is benign or malignant. So if it belongs to a benign or malignant class. So we want just to understand to classify this kind of image, and we're going to see if the region of that indicates the presence of a tumor, if this tumor is benign or malignant. But we can have many other kind of examples, for instance, optical character recognition. So in which the image corresponding to each of the alphabet, each letter of the alphabet has to be recognized among the 24 Latin alphabet letters. So we have 24 classes. Or another example, for instance, could be the prediction of authorship of a given text. So given a text written by an author, we want to predict who is the author of that text among a number of authors. So in this case, the authors represent the classes of our problem. So, and we can have a lot of other examples like music classification, in which we can classify, for instance, the genre, the author, the song, and many other examples that we can have the opportunity to see. So in this kind of task, the task of classification, the first step is understand how to design a machine learning task, how to decide the way to represent each pattern, so each group of input sample for our machine. So we want to understand what is the best way to give input to our algorithm. And so to this end, we should encode the information. So we try to extract the information from our raw data in the best efficient way. So we need to extract the most significant information from our input data and pass it to our machine. So this process, this is usually done by transforming the raw data in a new space with each pattern, in which each pattern is represented by a vector, which is called a feature vector. So we start from a pattern, so from some input samples that are that represent the input data, and we want to extract only the fundamental, the most significant information from this data. So we can extract these features and store them in a feature vector, which is just a vector. So the elements are just called the feature and represent the most significant characteristics of the original data in some kind of transformed space. So we want the goal of this kind of transformation is to represent a large amount of data with few features. So we are trying to only take in the most significant part of our input data, and we are going to represent it in some kind of forms that can be passed, that can be analyzed by our machine learning algorithm. So if you remember, we talked about signals as some container. So we have a signal as a container of information. So imagine that you have your signal which contains some information, and you have a lot of information. So I imagine that you are going to process some kind of streaming signals, or if you have a lot of data coming from sensors and so on. So you need a lot of computational resources to process all the data and try to have your decision, for example, for classification and so on. But what is the best way to optimize this process is to take only the most significant part of that signal. So imagine that from this container you just take the most significant part of the information, and you want just to process this information in some kind of transformed way. For example, we will see a lot of examples of features from raw data, and we just take some kind of form of this signal and put it to our algorithm. So each pattern becomes in this way as a single point in a new space, and this new space is called the feature space, or the input space. And we can refer to this process as a feature generation stage. So this kind of transformation from raw data to features is called a feature generation stage. And we can usually start with some kind of larger number of features in order to be sure that we are extracting the most significant information, and then we can just select the most useful features among those extracted, and this process is called the feature selection stage. So we have this is the first step that we are going to approach in our problem of classification. So once we perform the feature extraction problem, the feature extraction process, we are going to decide upon the input space, upon the new space. We need to take the new step, which is training the classifier. So the classifier is our algorithm, is nothing but our machine learning algorithm, and we need to train the classifier. What does it mean? Do you have an idea of what does it mean, training a classifier? Anyone? So if you remember, for instance, the Adeline video. So if you remember the first lesson, I showed you a video of the Adeline machine, which is one of the first machine learning algorithms, machine learning. So in that case, machine, because we can saw a very big machine. So we have in that video an example of the Adeline classifier, in which we have a TJ pattern problem. So our machine is going to if the man if the man put as input a J or a T pattern. So one of the first step is to give some inference to the machine. So at an initial phase, at that initial stage, the man is going to tell to the machine, okay, this is a J and this is a T pattern. And this problem is called this phase, this process is called the training stage. Once the training stage is as performed, so and the machine has understood what is a J, what is a T, then the man can just put any J or T pattern in the machine, and the machine is able to recognize with some kinds of output if the pattern put by in input by the man is a J or a T. So the training stage is very important for a classifier, because we are transferring to the machine some kind of inference. So we are going to give some instruction to the machine, some kind of supervision to the machine, and we are going to be a teacher for a machine that still does not have any knowledge about the output and the input. So we are going to say, okay, this is an example of the J pattern, this is an example of the T pattern, and we're going we want that the next pattern is automatically recognized by the machine. But the first stage is called the training stage. So how is achieved this process? So this is achieved by selecting a set of data, which is called the training set. So the training set is nothing but the examples that we are going to give to the machine. So all the examples that we give to the machine in the first stage is called a training set. And so we can consider a set of pairs X and Y with a number of a number of examples. So in this case we have that X is our input vector. Imagine that it is a vector of features in particular, and Y is the output variable. That is nothing but some kind of variable that denotes a class in which the input belongs to. For example, X in the previous example may be a J or T pattern, and Y is just the label, so the class of the input. So if this is a J pattern, Y is J. If it is a T pattern, so imagine that all the points that can build the T, so our class is a T. So we have some input data and some output class, some class that define the class label for our data. So the class labels Y takes values of our discrete set. For example, some kind of just numbers, discrete numbers. For an M classification task, we have a number of M values. So imagine that we have 3 classes. We have just that our values can be discrete. So take 1, 2, or 3, depending on the class that we are going to evaluate. So once the training stage is finished, so once we have given our inference to the machine, we are ready to pass a new input to our machine, and having a result. So once the classifier has been designed, the system is ready for prediction. So we are going to put an unknown pattern to we can pass an unknown pattern to our machine, and we can achieve some kind of results. So given an unknown pattern, we form the corresponding feature vector from the raw data. We can give this value to the classifier, and the pattern, so the new pattern is classified in one of the classes. So in order to understand better this kind of example, we can go a little bit into detail in the explanation of what is the classifier. So it is possible to design a function that is able to predict the output label. So we have our data and unknown pattern, and we want to have the right output label, so the right classification of our unknown pattern. So we need to design a function that is going to understand if our pattern is a J or T pattern, and this function is known as the classifier. But the classifier is nothing but our machine learning algorithm. So our machine learning algorithm is nothing but an algorithm that is going to create a function, and this function must say if an input pattern belongs to a class rather than another class. So once we finish the training stage, we can focus on the classifier function that that can build in the right way in order to put the right result. So in general, we need to design a set of functions. So we are going to start from so we are going to think that at the first stage we don't have any information about the function. So we start from just a basic function. We can have an infinite possibilities of this kind of function based on our input. So in the training stage, we have some kind of example, and we are going to to train our classifier. So this means that our function can be designed a little bit better among all the possibilities. So we can arrive to a final function that is the right function that is able to perfectly classify some unknown pattern in input. So we can consider just a simple case to understand this process. For example, we can consider a two-class classification task in which we have some input pattern, and we want to classify this pattern and input pattern as one of the two possible classes. So imagine that we have two labels. Each label is associated to a number, for instance -1 and +1, but we can have also 0 and 1, we can have 1, 2, so it depends on what you are going to represent the output label. So instead of having just the description, the literal description of your class label, you can have just the number associated to the label. So in this case, -1 and 1. So once the classifier is designed, we are ready to predict. So we can have an example based on this two-class classification. We are going to I'm going to show this feature. So we start from we start from this kind of point, this kind of example of two-class classification. So initially we have two set of points. So this point, two set of points. So each one representing a pattern in the two-dimensional space. So we have x1 and x2. So we can have that the points represented by stars belong to one class that we denote as omega 1 class, and the points represented by crosses belong to the class denoted by omega 2. So these points are the training points. So imagine that you have your points and we are going to give, okay, this is a star and is classified by omega 1. Okay, this is a cross and this is classified by omega 2. So we have a number of examples and we can associate to each point, each training point, a label. So these are in the previous notation. Imagine that x of x are the point, x are the point, and y is the class associated to that point. So these are the examples. So imagine that this is a feature vector and this is the class associated to this vector. Okay, so once we have trained this point, based on these points, we classify a function. We built a classifier, so we built a function, and in particular, we are going to give some kind of learn to this function, some kind of learning to this function. So imagine that we have a line that can take any kind, infinite possibilities, so infinite form in a b-dimensional plane. But given the input, we can have a few number of possibilities for our classifier. So in the simplest case, we have that our classifier, for instance, in this example, can be represented just by a linear function, just by a line. So it is very easy to understand that it is a classifier, so it is a line that divides the region in two parts. So every point belonging to this part is classified as an omega 1 point, and each point belonging to this region of the plane is classified as an omega 2 point. So imagine that it is just the training stage. So imagine that you have a new input, so a new point, and we are going to understand if these points belong to the class 1 or the class 2. So here is the linear function that we can, by which we can represent this classifier. And so every point that is on one side of the line will give a positive value, and all the points on the other side will give a negative value. So positive values are classified by omega 1, negative values are classified by omega 2. So it is very easy to understand this kind of classifier. So it is very intuitive classifications, because our classifier is just a linear function. So imagine that we finish the training stage and we are going to classify a new input. So we have a new point that is denoted by a blue circle, whose class is unknown, and we are going to say if this point is classified as omega 1 or omega 2. But if we suppose that it provides, given this new input, the function provides a positive value, we can classify this point as belonging to the star points, so belonging to the class omega 1. So I guess it is a very simple example, but it should be clear to everyone. So if you have some doubts about this kind of example, please let me know, because it is a very basic example of classification, but I'm going to be sure. I want to be sure that it is easy. It is understood by all of you. So I can just repeat. So this is a training stage in which we give all the inputs and classify all the input according to the points. So the start points are classified as omega 1, and the cross points are classified as omega 2. So I give a certain number of example for omega 1 and another number of example for omega 2. Given this point and the classification, I'm going to learn a function. So what does it mean, learning a function? It is a linear function, and just the important thing is to understand the value of the coefficient of this function. So based on the example, I can put the line in the right position, just changing the coefficient of, of the function. And these coefficients are uh, computed by a machine learning algorithm that put in the right way this function. So once we define the function from the training stage, we are going to give the prediction. So if we have a new point, based on the results of the function related to the x to the new point, we can say if the function gives a positive value as we have a zero, we have a point in the class 1, and otherwise we have a point in class 2. So this example is very easy to understand, but basically it represents uh, the process of a classification task. So it is very intuitive, but we can understand what is a classification problem. So we start from some data, we transform the data in some kind of feature. So we extract only the most significant information from this data. We train a classifier, so we give some example to the classifier in order uh, to find the right coefficient that can give the best line that separate the two regions. And once we have the training stage, once we finish the training stage, we are able to predict based on our function the new input. So if we have a new input based on the function, we can say if this input belongs to the class 1 or the class 2. Is it okay? Anyone can give me some feedback? Okay, so I can go. Okay, so I can go. It's 3 dimension. Yeah. So this is a very simple example in 2 dimension. So it is just a basic example. Imagine that we have 2 dimensions. So we have a bidimensional plane here, and we have x1 and x2 only. So each point is represented by coordinate x1 and x2. We will have some more complex example also in three-dimensional space and so on. But this is just some example in order to understand what is a classifier. So what is a classification task? Yeah, you're welcome. Yeah. Yeah. Okay, so imagine that in this case, you are going to learn your function in the way that all the input uh, can be so all the output of this function can be positive or negative, but not equal to zero, because you are going to define this function in this way. But imagine that you have a point on this function, you have some kind of output that is has some kind of uncertainty. So we can go later in this course this kind of problem, but probably you are not able to understand well that point. So you can say that that point belongs to omega class with an accuracy of the 50%. So it cannot be classified with a maximum accuracy. And this means that we are going to set our classifier a little bit better, and we can try to find a better function that represents our classifier. So a better function that is going to separate the points in the plane exactly. We will see later in this course some kind of examples in which it is not possible to separate perfectly by a line, but we need to create some more complex function that is able to separate the points from one class to another one. So this is just a simple example in which it is very easy to understand if a point belongs to one class rather than another. But we are going to see that, of course, in real problems, it is not so easy, and we are going to design a very complex function. So we need some kind of sophisticated machine learning algorithms to separate the planes or separate our regions, our feature regions, in order to have a correct classification. So we can also imagine that you have some points that is not that cannot be classified. If we have some kind of supervision that we can also improve our function, and we can just say that, okay, we can just move the line down or up depending on the right result. We can continue the training stage depending on the problem that we are going to tackle. But we can see a lot of these examples later in the course, so we have the opportunity to see how to complexify our problems. So I would like to show you some kind of application related to classification. So we can have some examples of real-world application in which we have classification problem. So classification, as I said, is one of the most widely used form of machine learning. We can solve a lot of real-world problems by classification algorithms. So I would like to give you some very simple examples related to real-world problems, but of course we can have imagine a complexification also of this kind of problems. So one of the example can be, for instance, the document classification. So document classification, in document classification we want to classify a document that can be, for instance, a web page or an email message or any kind of other text that can represent a document. So we have a number of classes. See, what does it mean that we can have I don't know, a number of documents, kinds of documents. So, for example, a web page or other kind of documents. So a number of C classes, and we are going to read a document and classify the text. So if one text is belongs to a web page or an email message or any other kind of classes. So our input data is nothing but text. So we can have input data as a text. So our signal in this case is represented by text. We need to extract some information to this text, and we're going to train a classifier, and we're going to have the right classes for our new input. So a special case of document classification is email spam filtering, which is a two-class classification in which our text is just classified as spam or ham. So if we have some kind of useful text or some kind of spam email, so essentially we can have some message. For example, we may notice that most spam messages have the high probability containing some words like I don't know, buy something, or I don't know, some kind of Viagra and so on, some kind of messages like this that can be easily classified as spam and so on. So it is an example of two-class classification problem like the one I showed you before. And most classifier can assume that the input vector has a fixed size. So we can we can transform our input vector, which is text, as in a feature vector format, which can also known as a bag of words representation. So if we have variable length documents, so we can transform these variable length documents in a bag of words representation, and so we can try to have some input vector with a fixed size, and this feature vector is nothing but a representation of the text, and it is called bag of words. So how it works? So the basic idea is define some kind of number associated to the input. So we can set x ij equal to 1 if the word j, if and only if the word j occurs in document E. So we have some kinds of numbers related to the occurrence of some words in a certain document, and this kind of transformation results in a binary document times word co-occurrence matrix that can be represented in this kind of figures, in this kind of figure. So it is something like a strange figure. So it is nothing but a matrix in which we have a binary matrix in which we have documents and words. So imagine that we have some kind of occurrence, and each line of this matrix is a document. So based on the color that can go from white to black, each color is related to the occurrence of a word in that document. So each row of this matrix is a bag of words vector, so is a feature vector of some kind of text, and we can try, based on the pattern that we can see in this matrix, we are going to divide to understand that we have four regions. So we built 3 lines, 3 classifiers. So we basically have we can have one classifier that divides the whole matrix in 4 regions, and each region is related to a class. So for instance, it is very easy graphically to see that this class is very different from this other class if we're going to see some kinds of word that can occur in this class. So the documents of this class, for instance, has this kind of region that is completely different from the other classes, and so on. So based on these differences, we can classify the documents, and we can see, okay, these documents or this line belongs to one class or to another class, and so on. So it is a strange representation, but it is nothing but a representation. So we pass from having a document with a lot of text, we transform all the text in a bag of words, so in some kinds of number of occurrences for words. And based on the results, we are able to detect, to recognize if a document may belong to a specific class rather than another one. And it is a very common problem, a common real-world application. Another application, which is another problem, which is a toy problem, one of the first problem of classification, is classifying flowers. So flower classification is an application example which is originally due to a statistician which is called Ronald Fisher. So in this example, we want to learn to distinguish three different kinds of iris flower, which is called the Setosa versicolor and virginica. So these flowers belongs, all these flowers, the three flowers are iris flowers, so they are very similar, but they can be distinguished based on some kind of characteristics like sepal length, width, and petal length and width. So based on this basic character of the main characteristics of the flowers, we can extract the information, and based on the image, we just try to extract these main characteristics, which are nothing but our features. So in this case, from the raw data, which are the image of the flowers, we extract the main characteristics, so the main features, which are in this case sepal length, sepal width, petal length, and petal width. So here are the examples of the flowers. Here is the examples of the flowers, and we can see that Setosa versicolor and virginica flowers, they are very similar. So it is not easy to recognize if these iris flowers is Setosa versicolor, is an iris flower is Setosa versicolor or virginica, but we can detect the right classification based on the main characteristics, so based on the features that are the characteristics of the flowers, the distinctive characteristics of the flowers. So one of the way to have this kind of visualization of the features and have a good visual classification of these features is to have a scatter plot of the features of the iris data, and we can see that we can distinguish, for instance, the setosa, which is denoted by the red points here, the red circles. We can distinguish the setosa from the other two classes just by looking at one of the features. So it is a scatter plot, so a plot in which we have all the features and the combination of the feature. So if we look at just one feature, it is very easy to distinguish the setosa, which is the red one, from the other two. So we have the distance, it is very easy to see from this kind of plots. But it is a little bit harder to distinguish versicolor from virginica. So in order to understand these two classes, we just need to combine uh, at least two features, so we can see the behavior of versicolor and the virginica by looking at least other two features and see how they can behave and how they can be classified according to the features. But we can understand a little bit more into detail this kind of situation where we are going to put it in practice and see how to have this kind of plots and how to build the classification that separates these classes based on the features and build our right classification. And another example is, for instance, the handwriting recognition. So it is another problem of image classification. So handwriting recognition is the problem of isolated handwritten letters or digit. For example, if we have a letter and we are going to classify the postal or zip code, we can use the handwriting recognition, but we have a lot of other examples. There are a lot of data sets that are that we will use in this course in order to perform this kind of tasks. One of the most famous is the MINST, which stands for Modified National Institute of Standards, and we have a lot of examples. So here is some kind of examples of the handwriting recognition. So we can have some kinds of classes which is so we have some kind of digit in this case, and we can classify the digit based on the true class. So we are able to recognize a 9 rather than a 5 and so on. But we can have also a different representation of this digit. For example, we can have some kind of mixture of features and have a different representation of the same image. So based on a different representation, we are going to understand if this is a 5. Even if for us it is more easy to understand this kind of representation because it is easy for us to understand this is a 2. But for a machine learning algorithm, it also easy to understand that it is a 2. So it is nothing but a different representation, but inside this image we can classify some pattern that is able to train a classifier and to say that this pattern is different to this other one. So it's different from this other one and from the others in general. So every letter that can give an output similar to this one, a feature representation similar to this one, can be represented by a 2. So we have a different representation of images, and based on the representation of the images, we can have the right classification output. So I can move faster to regression task, which is the other task of classification of the supervised learning. So regression is very similar to the classification tasks, but it involves, since it involves in the same way a feature generation and feature selection stages. But the main difference is the fact that the output variable, so the y, is no longer discrete, but it takes some real values. in an interval of real axis of complex value region. So imagine that you have no you have any more you don't have discrete values like classes. So you don't have 1, 2, 3, class 1, class 2, and class 3, and so on. But you have continuous values, so you can take values in an interval of real domain or complex value domain, and so on. So the regression task is can be also denoted as a curve fitting problem, and we will see why it is called as this kind of problem. So the term regression was derived by a writer, Francis Galton, who in 1886 wrote an article which is called "Regression Toward the Mediocrity in Hereditary Stature." So in this article, he observed that the children's age is not passed by parents, but it regresses towards the population mean. So for a child, instead of taking the height of his mother or his father, so the child stature, the child height is going to regress toward the population mean. So it means that, for instance, if a child has very tall parents, it is not said that he's going to be as tall as his parents, but his stature or her stature can regresses toward the population mean. And this is the meaning of this word regression. So this regression task is a curve fitting problem, and this is the graphical meaning of curve fitting. So as in the previous state, we can consider a training set. So we have our input data and our output data, in which we have the difference that the output data is not a discrete value but can be taken in a real domain. So it is a continuous value taken from a real domain. So our function to be built in this case is a function that completely fits the data. So even in this case, we are going to understand what is. So in the previous case, we are going to estimate a function that is able to separate the two regions in the plane. Here we have a different problem, but as the previous case, we are going to estimate a function, but in this case, our function is going to fit the data. So imagine that in this case you have your training data are these points in the plane. So are these points that are put in this b-dimensional plane, and we are going to predict a curve that fits the data. And we can have, for instance, a linear curve that can fit the data, or can we have some kind of non-linear regression, non-linear curve, for instance, a polynomial curve that fits more the data. So based on our precision, based on our data. So basically we have some kind of problems that is built in a different way. So while for classification it is more easy to understand, okay, I have some inputs and I need to just to say if this input belongs to a class or another class. For regression it is not so, it may be a little bit harder to understand if I present you as a fitting the data, a fitting problem. But it is a very easy, as in the same way. You need to classify this this problem, just to see this problem in real application. And you can see that you have lots of examples of regression problems also in real world applications. And for instance, you have a number of problems that involve signals and input data. For instance, you can have a financial application in which you can predict the stock market prices given the current conditions and given other kinds of important information. So you can have a lot of other kinds of prediction application that involves the prediction of the age of a viewer watching a given video, the prediction of the location in the 3D space of a robot. You can predict the amount of some kind of tumor or some kind of diagnosis in some clinical measurement. You can predict the temperature in a location, and you can have a lot of problems that can be reconducted to this regression task. So regression task is very important because we can have a lot of application, and we can use this kind of algorithms in a lot of contexts. So so I always say that machine learning is not a matter of I don't know, one context rather than another one. So machine learning can be useful for computer scientists, can be useful for electronics engineer, can be used for biomedical engineers. So machine learning can be used in a lot of different contexts because you can always find problems that can be reconducted to classification rather than regression. So based on the approaches, you can apply your algorithms in different contexts and in different applications. So it is very important for you to understand the capabilities of machine learning algorithms in order to be applied in a very easy way in different contexts. One of the contexts, for example, can be the restoration of the restoration task, which is also a regression task. So we want to deblur an image. So imagine that you have your cameras and you move while you're taking the photo. You have some kind of blurred image. We want to apply a machine learning algorithm that is able to deblur the image, so it is able to reconstruct the image and to remove any blurring effect without having the knowledge, the real knowledge. But how it is performed just by having some examples. So your algorithms previously had example of original blurred and deblurred images, and based on these examples your algorithm is able to perform this kind of deblurring from your camera. So this is another important application that you can find. So I would briefly also introduce, since we are going to finish, I'm going to introduce the other problem, which is the dimensionality reduction that we will see in a few applications, but we can see also in this course. So dimensionality reduction is, imagine that you have a high amount of data and you want to reduce the dimensionality based on the fact that you want to you have limited resources for the computation, or you have any kind of limited space, I don't know. So you may have a lot of motivation in order to reduce the input data in in a lower dimensional space. So you want to reduce the data, and imagine that you extract information from a signal. That information is too much for your algorithms, for your hardware to be processed. So you want to reduce the data in order to have the same performance of your classification or regression problem, but at the same time you want to preserve the right information in order to perform a certain task. So it is a simple example. You have some points in the three-dimensional space, and these points can be also represented by a projection on a plane. So having the projection of a plane, we are able to recognize some pattern. Of course, we don't have the same precision of the three-dimensional representation, but we are able probably to perform our task that can be regression or classification depending on the problem. Of course, we can further reduce the data in a 1D dimensionality problem, for example, in a line, but of course we are losing a lot of information and our accuracy will decrease a lot, and probably we are not able to give a right representation of our problem, a right performance, right classification, a right regression output. And one of these, the motivation behind this fact is that a lot of problems can be, a lot of data may appear in a high-dimensional space, but from all the data there may be only a small number of degrees of variability that is called latent factors. So imagine that we have our data, we have some kind of little movements from the data, and these movements are correspond to a degrees of variability that are called latent factors. For instance, we can have the modeling, when modeling the appearance of a phys image, we have some few latent factors that can be, for example, the lighting, pose, identity, and so on. And this is an example of latent factor for face recognition problems. And one of the common approaches to reduce the dimensionality is called the principal component analysis. So it can be seen as some kind of unsupervised version of a linear regression, because we are going to pass from our data. Imagine that you have your high dimensionality data. You put from this high dimensionality data to a low dimensional data that is called the Z, and from Z you are going to give your output Y. So this is a kind of regression, a classic regression problem. In the PCA, you are inverting the arrow. So based on your high dimensional output, you are going to interfere in the latent low dimensional vector Z, so that contains the features of the input. And based on the Z, you are going to reduce your input in order to give the right representation of the output of the regression output. You can have this kind of methods in a lot of applications, for example, in biology, natural language processing, signal processing, computer graphics, and so on. So we will have the possibilities also to have some kind of examples also in some lab sessions. Just to conclude, we have also some kind of application like missing data. So missing data means that you have values that can be unknown. For instance, imagine that you have some kind of sensors, and all the sensor collect some data, but you can have some void, I don't know, based on some damage of a sensor or some kind of any factor that can be interfere in collecting the right data. So you can design a matrix in which you have all the values collected by sensors, collected by any kind of input devices for your application, and you have some kind of holes in your matrix. So the goal of, for example, of imputation is to infer possible values for the missing data. So you are going to estimate the missing values, and this is called a problem of matrix completion. We will have definitely some also some example in our lab sessions. One of the example is imaging painting. I don't know if any of you is have some experience in Photoshop, for instance. You have a photo, an image, and you have some kind of obstacle. You can select the region and just clicking on fitting the region based on the context. You have the reconstruction of the image according to the missing value as to the values that you already know. One of the examples can be, for example, the collaborative filtering. Collaborative filtering is an example of prediction of the taste of a user. For instance, one of the most famous example is the moving rating data. For example, on your Netflix application and so on, you have some kind of movies and you have a lot of users, and each user gives some preference of its own preference of the movies, and based on the similarity between users, the system is able to suggest some movies to a new user that has similar preferences related to another one. So we can conclude here for today, and tomorrow we will have the first lab session. So it is possible to have the slides. Okay, so I forgot to say that I have uploaded the slides of this morning before the lecture. So usually the day before the lesson I uploaded on the website the PDF of the slides, so you can follow the presentation also on your slides directly if you are going to use your you take notes on your slides on your PDF. So we can conclude the lesson of today. Thank you all for being here today, and we can I can send you some emails with once I uploaded all the material on the websites. So thank you again, and see you tomorrow.